Let's talk about HBase. Unlike other systems that are just kind of bolted onto your Hadoop cluster, HBase is actually built on top of HDFS. So if you're storing massive data sets on an HDFS file system, HBase can be used to actually vend that to the outside world at very large scale. So what is HBase? It is a non-relational scalable database built on HDFS, which we already said. So just like every other NoSQL solution, it does not have a query language, but it does have an API that can very quickly answer the question, what are the values for this key, or store this value for this key. And it's built on the ideas behind Google's Bigtable database. So the dirty little secret of Hadoop, and well, it's not really a secret, is that most of it is built on top of papers that were published by Google about 10 years ago, where they actually spilled the secrets of how their infrastructure works. And Bigtable was a part of it, where they had the problem of storing information about links to all the web pages on the entire planet, which obviously is a big data problem. And they developed something called Bigtable to solve that problem. Now, HBase is just pretty much a straight up implementation of Bigtable where they just changed some of the names. So it's an open source implementation of the algorithms and systems described in Bigtable. And if you want to go look up this paper, you can just read the first half of it to get the general ideas, but I do recommend it if you do want to get into more depth of how HBase works, because HBase really is Bigtable, just in open source form with some different names. So like I said, HBase doesn't really have a query language. There's no equivalent of SQL that you can do on it. All it has is an API, so it can do what we call CRUD operations. Cute little acronym. That stands for Create, Read, Update, and Delete. So it offers transactional access to creating a row in a database, reading back the values of a row in a database, updating a row in a database, or deleting a row in a database. And that's about all it does, but it does it really, really quickly and at very large scale. That's the power of HBase. Take a look at its architecture here. So this is how HBase works under the hood. Basically, it's split up into different region servers. This is the core of HBase itself. And when we talk about regions, we're not talking about geographic regions. We're talking about ranges of keys. So it's just like sharding or range partitioning in more traditional database systems. But the magic of it all is that it can automatically adapt. So as your data grows, it can automatically repartition things, and if you add more servers to the mix, it can automatically deal with that at runtime. So there's a very complex mechanism that involves write-ahead commit logs and merging things together over time asynchronously, but you don't have to worry about those details. HBase does it for you. So all you need to know is that it can automatically distribute your data amongst a fleet of region servers, so an entire cluster, if you will. And these are all sitting on top of your HDFS file system, which itself is distributed, right? So you can have HDFS hosting very large files across an entire cluster of computers that are broken up into blocks. And again, some of what HBase gives you is taking all these little tiny records that are in your individual rows and clumping them together into larger files, which are better managed by HDFS. So again, it's all transparent to you. Now, when you have an application that's actually talking to HBase, say a web application or a web server, it's not actually going to talk to these master nodes up here directly. It's going to be talking to region servers directly. But these master servers up here are what keep track of the actual schema of your data, where things are actually stored, how they're partitioned. This doesn't have to get queried very often, so it's not really going to be a bottleneck, but it is sort of like the mastermind of your HBase cluster that knows where everything is. And that in turn depends on a technology called Zookeeper that we haven't talked about much yet. But you can kind of think of Zookeeper as a case of who watches the watchers. So it's a highly available system that can keep track of who the current master server is for your HBase instance. And if one master goes down, Zookeeper can keep track of who to go to next and tell everyone about who the master is. So that's it at a high level. The key here, though, is that it's partitioned amongst different region servers. There are mastered servers that keep track of where everything is, and the data itself is actually stored on big files on HDFS. So let's talk about HBase's data model. Like with any database, it's going to have this concept of rows, where each row is identified by some unique key value. So for example, you might have a database of customer information where the rows are identified by a unique customer ID key. If you're coming from the relational database world, that would be the primary key. And each row contains information associated with that key. So for example, a customer database table might have rows identified by a customer ID, and it might have columns that map to the customer first name, last name, address, zip code, all that good stuff, right? Now, what's different about HBase is that it has the concept of column families. So you don't define a fixed set of columns for each row in your database. Instead, you define column families, and each column family can contain a very large number of individual columns. And this comes in handy where you have cases of sparse data. For example, let's say you have a database of movie ratings broken up by each user, and we'll actually do this as an example later on. You don't want to have to actually store a column for every single movie that was ever created to hold the ratings each user has for each movie. What you can do instead is create a column family for ratings as a whole, and then have a large number of columns that map to each individual movie, but it's okay if each customer doesn't have data for every movie. The power of HBase is that it can deal with sparse data like this, so it doesn't actually consume any space to have a column that's missing data. So the model that you usually want to think about with HBase is how can I have a very small number of column families associated with each row of my database, but then I can actually blow up each column family potentially into a large number of columns. And you don't have to either. You can have a one-to-one mapping as well. So you can have a column family that's just customer name and leave it at that, and that's going to be your column. But you do have that power of splitting up a column family into potentially a very large number of columns, which may be populated in a sparse manner. Now, we also have the concept of a cell that's given by the intersection of a row and a column. And another cool thing about HBase is that it can have many versions of each cell. So it can actually store a history for each cell in your database table. And it can do that automatically based on timestamps. So you can actually say, store all the information that was given within the last week for this given row column intersection. And you can also just say retain this many versions of a given cell. So for example, keep the last 3 values that I saw for this particular piece of data. It makes more sense when we look at an example, right? So let's do that. Let's look at the problem that Google actually was trying to solve with Bigtable, which became HBase. They want to be able to track all the links that connect to a given web page. So let's say they're trying to figure out who links back to CNN.com. This is what their schema might look like in Bigtable, or HBase in our example. And this comes straight out of the Bigtable paper. So they might have a key that is a web page or a website, and they actually store this in reverse order. So instead of www.cnn.com, they do it backwards in com.cnn.www. The reason is that keys are stored lexicographically within HBase. So if you're trying to minimize disk seeks, and you know that you might want to have different web pages on the same web server, you might want to do something like this. So sometimes you'll see www.cnn.com or si.cnn.com. There might be variations on www, and you want those all to be together within the database. So that's why they do things like that. Sometimes those little choices of how you actually structure your keys or structure your columns become important when you're dealing with scalability issues. And what does their actual columns look like? So they've set things up into a couple of column families in this example. One is the contents column family, and there's only one column within this column family, contents itself. But you can see they're using the versioning feature to actually keep 3 copies of the contents of this page. So they're actually scraping CNN.com and storing the last 3 incarnations of that page that they came across, the last 3 crawls. And who knows what they're really doing under the hood today, but this is what they're describing in the paper. And then they have a anchor column family. So this is where they're storing all of the pages on the web that link back to CNN.com. And here's a couple of examples from that. So the syntax for describing a column in HBase is column family, column name. So anchor, cnnsi.com would represent a link from cnnsi.com, and anchor, if you will, back to the key cnn.com. And what they actually store within that column is the anchor text itself. So for example, someone put the word CNN on a web page on cnnsi.com, linked the word CNN back to cnn.com. That link text is what actually gets stored as the column value. And as another example, let's say a website called my.look.ca actually also linked back to CNN, but they actually linked the word cnn.com. There's an example of where we're storing anchor, the column family name, the actual website, and then the actual anchor text there. So you can see here that they have a column family that's just called anchor, but this column family can contain a huge number of columns, right? I mean, basically every website on the internet is a potential column under this column family. And it becomes very important in this sort of a use case to make sure that you can store that data sparsely, because you don't want to have to store the fact that CNN.com is not linked to by 5 million other websites, right? You just want to be able to store the actual websites that do link back to it. So that's the power of this particular data model. There are many ways to access HBase. One is through an interactive shell. So if you're actually logged into the server that HBase is running on, you can type in HBase shell and interactively create commands to create new tables, create the column families in that table, and so on and so forth, or drop tables, do whatever sort of maintenance you need to do. But for runtime, to actually use the power of HBase, you're usually going to be accessing it from, some service of some sort. So you're going to have some web server that's trying to put together a web page based on this data or something. So at its lowest level, there's a Java API for HBase, because HBase is itself written in Java. And if you have a Java-based web server or application, then you can talk to that directly. There are also wrappers available for other languages like Python and Scala, for example. There are also connectors available between HBase and things like Spark, Hive, and Pig, and we'll look at Pig shortly as an example. Usually what you're going to end up doing is writing your results into HBase from these systems. So you can do things where you're doing some sort of complicated transformation or trying to build up a specific view of the data within a tool like Spark, Hive, or Pig, and then outputting that into HBase so that it's accessible at scale to your web servers or what have you. There are also services that you can run on top of HBase if you don't want to be talking to it directly. So there's a REST server built into HBase itself. You just spark it up, and then you can communicate with your HBase database through a RESTful interface. REST is just a way of getting service results through HTTP requests. So it's a very easy way to do it. There are also other formats that we can build on top of that. These are basically called protocol buffers. Thrift is a popular one that was built by Facebook, I believe, and Avro is the protocol that is actually defined by Hadoop itself. So the advantage of Thrift and Avro is that they can represent data more compactly because it's more of a binary format, and you can actually store things more efficiently and transmit it more quickly as a result. The downside is that there's a tight coupling between the client and the server, though. They both have to know what version of Thrift or what version of Avro they're using, and it's pretty easy for things to get out of sync. So to keep things simple, REST is often a good choice, but if you want the maximum performance, Thrift or Avro is worth looking at. So let's go play around with it a little bit, shall we? Let's actually create an HBase table and query it through Python through a REST service and see how this all fits together.